Hello folks. Today we're going to be talking about the atoms and elements. Now I'm going to approach this slightly different than the book I gave you. So our book has us starting with the electrons and electron structure. Now they chose that for a reason to go this route. So technically speaking, even though this is an introductory class and an entry level into chemistry, most people already know what the atom actually is, or a general idea of it is. So they chose to go this route simply because of that. But I decided I'm going to go back and treat it like we kind of normally do it and do the atomic structure before the actual electrons. There's no real reason we had to do this order. It feels a little bit more normal to go backwards from how our book is approaching this. All right, so what I want to start out with is talking about what the atom is and how we came up with the idea. So Dalton was a scientist around the turn of the 1900s who actually did a lot of his proofs and such based on other people's works, but he was looking at various different ways to decide what was going on on the element and compound structure, and he came up with his atomic theory. And he is the person who coined the phrase atom, and he did just actually identify as a very tiny piece of matter. Now, he technically actually clarified it later on in his theories, and we do agree with this now, that the atom is just simply called, it's the simplest thing that retains the chemical identity of whatever molecule you're looking at, or whatever atom we're looking at. Now, I'm going to go back here, because I'm going to be using the periodic table some, and that's really what we're showing here, is the 118 atoms that pop up here in the periodic table are the only known elements, and it's very unlikely we'll get very many more, because you notice on the bottom of this periodic table have all these that are hollowed out. Those are ones that have to be lab made. They don't exist in nature, and all of them kind of fall apart in a few milliseconds. So to go to the next row, we're predicting the same type of idea. So we won't be seeing any new atoms, or very unlikely we'd find new atoms that have any substantial difference in their life expectancy. All right, so what is the atom? Well, it is, like I said, the simplest thing that retains the chemical identity, and it is kind of unique in the sense that if I go back here to the periodic table, every single one of these atoms, the two-letter symbols or one-letter symbol, have a single number above them. That single number represents the number of protons found in the atom, and they are all unique. 1 through 118, there are no numbers missing. If I somehow remove, go here to oxygen, if I somehow remove one of those 8 protons, make it 7, it's going to change the chemical identity to nitrogen. They are that unique, and they don't easily change outside of nuclear reactions. Alright, so what is the atom made out of? Well, it's 3 things that we care about in chemistry: protons, neutrons, and electrons. The physics people are looking into how protons, neutrons, or electrons are made out of. That's what those super colliders are for. But outside of chemistry, that doesn't really help us, because chemistry, we need those protons to make the atom to give the chemical identity. And they need to be grouped together in one of those 1 to 118. Think of the neutrons as kind of the glue. As soon as you have 2 protons in an atom, you need at least 2, sometimes more, neutrons to help hold it together. And we will find out that as soon as you have more than 1 proton, you have to be stable, you need to have at least 1 neutron for every single one of those protons. And as we get further down the periodic table, there are even more. Now, we will see how we figure out how many neutrons are in there, but we do expect that they're always there. Now, electrons are found on that outer shell, or the electron shell, and they are a negative charge. The charges are perfectly in sync with each other. We can actually get them and calculate it out, and it's just the only difference is the positive and negative aspect of it. And in a neutral atom, the number of protons and the number of electrons are identical. Now, when we back up and cover that electronic structure, we'll talk about how that changes, how the number of electrons can vary, and it will still have stability. It'll still be at a sodium atom, for instance, can have the exact same number of electrons as protons, or it can be below it with no problem. All right, so how did we figure all this stuff out? After Dalton came up with his theory, we had a bunch of scientists that actually figured out how the thing was put together. Because when they first thought about the atom, I just draw a little picture here, they kind of viewed it as a space of goo, positively charged goo, that had small little electrons floating around in there. Now, they knew what the electron is long before they knew what the proton was, because we could get them to come off. That is essentially what creates electrical current. We even kind of had an idea of how big they were and their charge. So we knew a lot about the electron, but we didn't know what the atom was. So they thought they had these little tiny particles in there, and this was just kind of a positive goo. Well, Rutherford was the guy that actually going to figure out what it was made out of. He's going to bombard gold with particles. Now, chose gold because technically speaking, it's the best metal to get really ridiculously thin. It can be quite malleable to the point where it's transparent. Have you ever seen a product called gold foil? It actually is gold. It's just so thin you can actually see through it like foil. Well, what Rutherford did is he put that gold foil in there, and then he bombarded it, beam of particles. These are actually alpha particles. Alpha particles are relatively big, and what he was expecting is, for the most part, they're just going to go right through that foil. Because, go back here to this picture, we thought this was just big, huge positive goo with an occasional electron in it. And they knew roughly that the electrons weighed about 1/1000th of a hydrogen atom. And then Rutherford's alpha particles weighed about 4 times the hydrogen atom. So he's expecting these to just fly right through. All right, but what they found as a very big surprise, or what he found as a very big, huge surprise at the time, is quite a number of them fully bounced back. Now, we kind of know why that is now. So a gold atom isn't just a bunch of empty space, and it's definitely not a goo. And the dead center of the atom is the nucleus. And matter of fact, on a gold atom, it's actually a pretty big nucleus. I said that alpha particle weighs about 4 times the hydrogen atom. Well, a gold nucleus, down here, weighs about 200 times a hydrogen atom. That's what that number down there kind of represents roughly, is that actual mass of one. So they were huge by comparison, which is why it was bouncing back. But as simple as this idea is, you bombard a piece of gold foil with alpha particles. This was what actually helped us understand how the atom is made. That's how we come up with the idea that the atom has a very densely packed nucleus with the protons and neutrons in there, and the electrons are actually going around around it. And technically, that's probably something some of you learned maybe as far back as 5th grade. Might not remember 5th grade, but you probably do remember that, yeah, okay, that does seem familiar, we did learn that. Well, on the atomic scale, we generally just point out that protons and neutrons have a mass of roughly 1. Now, technically speaking, it's not quite 1. Slightly off that. Neutron is slightly heavier than a proton, but we typically just say 1. Now, where that 1 atomic mass unit came from was we just decided back in the day that the carbon, which we knew had 6 protons and 6 neutrons, weighed 12 AMUs, atomic mass units. That's where this 1 AMU comes from. And just over the years, we got more fine-tuned and proved a few different things and found out that on that scale, if the average carbon does weigh 12, then these masses are slightly different. And we don't need these masses for any calculations we're going to use. They're just more interesting. Same with the mass of electron. We, in general, are going to say an electron has pretty much 0 AMUs or 1/1000th, because that's roughly close enough for what we're saying here. Now, location is kind of interesting. Location. We have these two in the nucleus, and these are in the electron shell. And then finally the charge. We have a +1 for the protons and a -1 for the electrons and nothing for the neutrons. And I have that nice little summary right here. And these little symbols, we do see these a lot. The positive and the negative on there, you even sometimes see these with little, they'll actually write out the 1 there, and then they'll put the 1 on those. actually, let me expand that out. I don't like how that looks. So we'd have the +1 and a 1. On the neutron, we'd have a 0 and a 1. And on the electron, we'd have -1 and a 0. And what they're showing is the charge and the mass. You sometimes see it that way. That's not wrong. It's just a different way of doing the symbol. But generally speaking, the P, the N, and the E are typically enough. Now, oftentimes we will see the E with the negative. They don't typically just write an E. But generally speaking, if you see that, that's what we're assuming that they're talking about. All right, so little possible questions type of thing. We got the protons, neutrons, electrons are a possible answer. Which one of these is found outside the nucleus? Well, that is the electron. Which one has a positive charge? That would be the proton. Neutral is the neutron. And found in the nucleus, well, that's the proton and the neutron. All right, when we look at the periodic table, I already mentioned that we have the protons listed there. Now, the protons, another word for that single number, is the atomic number. The atomic number is just the number assigned on that periodic table. It's also telling you the exact number of protons. So sodium, for instance, always has 11 protons. And if I go here, carbon, which we talked about earlier, 6 protons because it has a 6 above it. And go back to gold, another one we talked about, has 79 protons because there's 79 right above it. But that is the atomic number, which is why it says right there. Got the name followed by the atomic number and the symbol on our periodic table. Now, the next thing that we actually tend to see along that is, I don't want to do those yet, is the number of electrons. Now, at first, we always start talking about neutral atoms. So if the atom is electrically neutral, then the number of protons equal to the number of electrons. So if you're dealing with aluminum, and you look at the periodic table and see that aluminum has a 13 there, if it says it's a neutral aluminum, then that guarantees it also has 13 electrons. Now, something weird happens next. So the mass number is not something we find on the periodic table. Now, you're going to find something near it. What I mean by that, and I'm going to pick on carbon because we already talked about it. We said that carbon-12 had a mass of 12 AMUs, and that came from the fact that it had 6 protons and 6 neutrons. Well, 12 is also the mass number. So carbon-12, that tells me the mass number. Now, where that's interesting, on carbon, there's also a carbon-13 and a carbon-14. You might have heard about that one because they talk about it with radioactive dating. When they determine how old something is, you do carbon dating. Well, that measures the amount of carbon-14. Carbon-14 is not stable. It over the years will break down. It'll lose its mass and become a different element. Well, carbon-14 still has 6 protons, and that's because all carbons have it. But to get to that 14, we had to add 2 more neutrons. Because it turns out that mass number is just the sum of the protons and neutrons. Protons and the number of neutrons. Now, what is interesting, remember I said there's a carbon-12 and a carbon-13 and a carbon-14? If you look on the periodic table, you do see a number similar to 12. See that 12.01? Over here it says that the atomic weight. Now, you will generally find that the atomic weight is very near the mass number you're dealing with. But what happens is, carbon, for instance, is found mostly at carbon-12, which is why the atomic weight is almost 12 on the nose. 12.01 if you round it to 2 digits. That's really because that carbon-13 I was talking about, very rare. Only about 1% of the time do we find carbon-13 in nature. And carbon-14 is even less. It's always just a fraction of it. But what I have there is further down here. The atomic mass. Now think of the atomic mass as just an average of all those those mass numbers for various different atoms. Now quite a few have more than one stable isotope. And what ends up happening is the scientists have to look at all the ones that are stable. Lithium, for instance, there's a lithium-6 and a lithium-7. When they look at the average atomic mass, they got 6.941, which is why that's on the periodic table, 6.941. So think of these values as averages. And if you look down here at the bottom, all those ones I said earlier that are hollowed out because they're lab made, they have those brackets. The brackets are there because they're showing the mass number of the one that's easiest to make, or that's most likely to be made. It's definitely not the only one, but since there's no natural supply of those, there isn't an average mass. The average mass only applies when you have enough to actually generate more than one isotope. And some of them have a lot of isotopes. We find out later on in nuclear chemistry that when you have an even number of protons and you have an even number of neutrons, you're very stable. So you see how this is even, and even, one odd. But when you have an even number, you tend to find a lot more stable isotopes. So on the periodic table, that really does mean everything in this row has an even atomic number. There's more stable isotopes of those than there are one before. So they have a lot more range, or not a lot more mass numbers available. All right, now how we end up seeing this is just in that results. We're never really going to need to figure out those isotope ratios. We're never going to have to figure out that atomic mass. It's just going to be given to us. What we need to remember just, though, is that even though it's 35.5, what that doesn't tell us is the mass number. It doesn't tell us that there is a chlorine 35. It kind of implies it probably is, but this is an average. And that's why we find, turns out, chlorine there's a 35 and a 37. We're not going to need to know that, so I would provide the mass numbers if I needed to know there's a chlorine 35 and a chlorine 37. Other than that, we're mostly going to use the atomic mass because it's more of an average of what we find in nature. All right, skipped over a few things. We're going to look at these for summaries. So we have the number of protons, which is the atomic number. The mass number was the protons and the neutrons. And we're going to use that mass number to get the neutrons by just doing subtraction. And we're going to be able to find that a weird term that I skipped over, isotopes, is just when those neutrons vary. So what does that mean? If I'm looking at zinc, has a mass number 65, and I asked you how many protons it does have, you would know, well, if it has a mass number 65, I know that's not the protons because zinc has protons and neutrons added together to give the 65. Also know there's not 65 neutrons because this is protons and neutrons. All right, what I do need to know to figure out what the protons is for zinc, I need to look up on the periodic table what its atomic number is. So I find zinc on the periodic table, it's right here, and I have a 30 up there. That 30 simply tells me there are 30 protons, and 30 is the atomic number. And then to get my neutrons, I'm going to take that mass number and subtract the 30 to get 35. And then my last one, what's the mass number? If zinc has 37 neutrons, well, the mass number is the protons plus the neutrons, so I'm adding 30 to this to get 67. All right. Now, if I back up here, just want to figure out the number of protons. I typically don't give you a lot of information, just as nitrogen, sulfur, barium. I might give you a mass number, but the mass number doesn't matter. That would be like unnecessary information, is what I mean by that. I could say carbon 12, or carbon 13, or carbon 14, those three carbons I were talking about. But if I'm asking you the number of protons, we're looking at the periodic table, finding carbon, seeing that 6 there. And all of these have 6 protons. So nitrogen, for instance, there's a 7 right there. Oh, 7 protons. Very straightforward. We're looking right at that periodic table. Now, I know in some cases you might have seen it where we're going to give you a periodic table that might not have names or miss anything. You're getting this table just like it is on this. Every single test you get, the practice test, you get this periodic table. Matter of fact, it has some things on the back that you might come in handy. But the periodic table will have everything as complete as we need it to be. All right, I skipped over the first part of this. Your book actually focused on the electron shell now, and I'm going to that now. Now, shortly after the atomic theory was presented, we started to have a bunch of scientists trying to figure out what the nature of it is and how it was put together. A lot of quantum theory was born back then. And Niels Bohr was the first person that came up with a relatively good quantum theory model of what was going on with the hydrogen atom. Got a Nobel Prize for that. But that's what we're looking at here. It's talking about the nature of that electron shell. So we said the atom was a nucleus followed by a big, huge electron shell. We're looking at what that electron shell is. Now, the electron shell, it's best at first to think of it as almost like a bookshelf. Now, what I mean by a bookshelf is we can put electrons on shelves close to the nucleus or higher up. These shells kind of represent how we see the behavior occur. Matter of fact, that's actually why the periodic table got set up like this. So this first row is like where n equals 1, and this is n equals 2, 3, 4, 5, 6, 7, etc. It just goes down. Now, what is really weird is when Bohr was looking at this, he kind of understood that this lowest shelf, even though it's got this big, huge gap, could only hold a few things. You can get more as you go up on that shelf, and that's why the periodic table gets bigger. You can put more on each shelf. And that's why this thing, this 5789, they actually fit here where that line is thicker. This periodic table is supposed to be really, really long. It's just not practical, so we leave that thick line there and then move that row down below. But it gets bigger the further you go down. And if we ever do come up with element 119 and 119, 120, and 121, we'll have yet another row down there. All right, but that energy level, it is called the energy level because that's kind of telling you how much energy's in the electron to put in there. Now, we see that happen on some of these guys. This first row of elements here, they very much don't like to have that extra electron in there. Lithium, sodium, potassium, rubidium, and cesium, and francium love to exist as positive 1 ions. They prefer to lose that electron, and because it's in that uppermost bookshelf. You have to have that extra shelf on the atom just for one little electron. And it's out there on its end, it's far away from the nucleus, it comes off relatively easy. All of these will react very rapidly. If you have the metal of them, they all react very rapidly with water. Matter of fact, the cesium and francium, the further you go down, because that last electron is even further out from the nucleus, comes off that much faster, they're right on the edge of dangerous. You put sodium in water, it catches on fire and may ever even blow up. You go further down, it's just much more rapid on how that behaves. No good videos on YouTube for francium, but that's because, see how that's got that nice little hollow number? It's because it's unstable. At any given moment, there's probably only about 2 grams on the entire planet. It's in the process of breaking down as it exists. So, if don't know how you'd go about getting a bunch, that'd be an interesting strategy to try to get even a gram or 2 to throw in water to see how it reacts. But those all like to lose that one extra electron. It'd be like this level's full and you had to put 1 electron there, or this level's full and you had to put 1 electron there, this level here and you had to put 1 electron there. So it gives it up relatively quickly. So this energy level helps explain some of the properties we see. Matter of fact, it even explains what's going over here. All of these in that group 17 like to gain electron because it doesn't need much more space. It just fills up that shelf. This is a full shelf. That's why we call those guys the noble gases, and we find them inert. They don't react very well. It's because they have a full shelf on Bohr's model. All right, as neat as all that is, it doesn't explain what's going on, because whenever you've seen the electron, they've drawn a bubble, and you might have seen it where we draw something that kind of looks like a flower. Now what we're drawing is how we expect to see the electrons move around. Now what I mean by that, we're going to have different shells for the electrons, and we can get more and more in each of those shells. That's what we were saying. And we see these nice little bubbles drawn often. They're nice and pretty. And they're great to try to represent what's going on. But we don't think of the electrons as moving around in orbits like planets do. Now, that has a lot to do with how the physics works at that level. There is something else going on, and quantum theory is just weird. And we don't try to fully map out what's going on our math because the scale is so small and the electrons are moving so fast. So we do these weird things where we map out where we typically find the electrons. So imagine, all right, we're going to imagine these things are moving around, and we're just going to take a momentary picture, a moment later another picture, and just repeat that over and over and over, and then just try to map out where we see the electrons most of the time. So we don't map the orbit, we call them orbitals because they represent where we think they are most of the time. So an orbital is just a probability being found. Now, you find these different ways. So you look on the internet and you find orbital, they'll just have the shapes drawn, and you might see that it's a 95% orbital or a 90% orbital, and they're just showing that's where the electron is 90% of the time or 95% of the time. But they have weird shapes. Now, there's not an unlimited number of shapes. There's only a few we see, and they're kind of neat. Like the simplest shape we see, we call it an s orbital. It's a sphere. It's a beach ball. The p orbital is where you imagine if you take that beach ball like a balloon and you twist it on itself, it'll get that little fold in the middle, or a node, and we have different ways of orienting it. But we see that all of these happen. We have this f orbital, and we have 3 different p orbitals, and they do kind of look like that when they go together. Now, where does this happen? It actually happens when I need to put more things on a shelf. So the simplest shelf only holds 2 things. You need that simplest orbital. And that's actually what's going on in that first row. This hydrogen and helium, the difference is 1 electron, but they're both in an s orbital. You go down in the next row, we have that s orbital, and then these guys over here are in p orbitals. So carbon has 2 electrons in an s orbital and 2 in the p orbitals. And it's just how the electrons get arranged that create that. Now, we're not going to do a lot with those. We're pointing them out to point out that they're there. The most critical thing that we need to look at is that the periodic table is laid out in such a way that we have these arranged so they're the same type of orbitals. But the critical thing is, when we're talking about valence electrons are used to distinguish how things behave. So when an atom is neutral, you have the same number of protons and electrons. But since electrons can be added and removed, we see ions formed. And what we find is something kind of neat. That first row, I said it likes to lose an electron. What's happening is it loses that electron to become more like the noble gases. Well, what we're saying it's losing is its valence electrons. It has that 1 extra electron, 1 valence electron. It likes to lose that 1 valence electron. If we go to the next row over here, beryllium and magnesium, since it's on that second row over, we say it has 2 valence electrons. And all of those like to lose 2 electrons because then they're just like the noble gases. Now, as we go through here, we do see where you can count over. You can say this has 3 valence electrons. You can see how these guys have 4, and down here they have 12 valence electrons just because that's the number. That doesn't guarantee they'd like to lose 12 electrons. What we find is these guys in this middle behave somewhat odd. They do lose electrons, but they don't necessarily lose all of their valence electrons when they react. Zinc, for instance, only ever loses 2. And so does cadmium. It only ever loses 2. Those 2 only lose 2. They don't lose all 12. Mercury, right below it, can lose 2 or just 1. But what we're going to talk about these guys later is we're going to point out that everything in this light blue doesn't necessarily behave in a way that's easy to predict. We're going to find different ways to actually figure out how many electrons they lose when they become ions. That kind of affects these blue ones down here. And we'll be doing the same thing with these, that we will have to have a weird little rule when we explain how they lose electrons. All right, when we get to the yellow ones, they gain electrons. Now what happens is, I could count over and go 1, 2, 3, 4, 5, 6, 7. And here in group 17, we could say all of these have 7 valence electrons. Now that seems weird, because that seems like down here this shouldn't be 7. Because bromine, for instance, if you count across, it is going to be 17. But something weird happens on valence. So I say, and you'll hear this said all the time, these guys have 7, because it turns out bromine and iodine, while they do have 17, these guys are harder to get to. So those 10 don't really count as accessible valence electrons. So we do say these just have 7. And the yellow ones, even carbon with just now 4 valence electrons, typically like to gain electrons and become that way. So carbon, for instance, can be a +4 or a -4. So it loses all 4 or gains 4 and goes up to that. It typically doesn't do that too much. Carbon typically we find doesn't like to make ions by itself. But nitrogen and phosphorus like to do -3s. Oxygen, sulfur, and selenium like to do -2s. And the halogens, fluorine, chlorine, and bromine, and iodine like to do -1s and gain those electrons. So 7 valence electrons, 6 valence electrons, 5, and 4. Matter of fact, if you find an old periodic table, and it's not hard to find them, you still see them printed this way, you'll see this group is actually called, I can't write on this page, it'll be called a 4A group, and 4B, or 4A, 5A, 6A, and 7A. And the 4, 5, 6, and 7A is telling you the number of valence electrons. So they called these A's. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then down here was 3B, 4B. They called these the B group. We stopped doing that because that was an old way of doing it. It did help with identifying the valence electrons, because the group number was the valence electrons. But gosh, it's just as easy to count across. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Now this whole thing where it talks about the energy levels on how many they can hold, that is kind of interesting. It's a way of expanding what's going on with this bookshelf idea. But it's not really all that critical right now. It helps us to predict what's going on in the shapes, but I was just going to do something kind of straightforward for us. So on the first shell, you can have 1 shape. You can have 1 because the n equals 1. On the second one, you can have 2 shapes. That's where the s and the p's come up. 3 shapes. This might be a high school chemistry thing, but you might have heard of d orbitals and then f orbitals. Basically, the number of the n tells you how many of these shapes are available. Now, we see that in that periodic table. If I look at the periodic table here, we have this weird general shape here. And I'm going to put some solid lines here, and then down here I have that big row there. Well, how they're laid out, this is where that s orbital gets filled. This is where that p orbital gets filled. These are the d's, and down here are the f's. And they're down at the bottom because we didn't actually get to the f's until we got up to where that n equals 4. They just weren't available. But that's some of what they're talking about here in that, that how they're allowed to be on there. We don't need to go into that much detail on quantum theory to understand what's going on. Because technically speaking, the chemical behavior, which is what we all care about, is really just based on the valence electrons. Doesn't necessarily matter that 7 valence electrons on that group 17 are in s and p orbitals. It's the 7 that's far more useful for us. Down here, it's nice to know that 1 electron is in an s orbital, but it's not as critical as knowing that it's just 1 electron because they're in group 1. So we don't need to focus too much on these shells. But if you do look into it, it's all kind of neat and interesting. It's quantum theory. If you're a big math geek, later on you start to calculate this, and you can figure out how these shapes were determined. Neat little process to build up on them. And the orbitals do kind of look cool, because I mentioned them. I may as well draw them out here. Actually, I'm not going to do that. I'm not that good of an artist. we can just do this, atomic orbitals, because the internet knows everything, and hit images here. And there's the pictures I like. So this is kind of interesting that as you go down, you see how there's one of these, there's 3 of these, there's 5 of these, and there's 7 of these. They just go up by an odd number. The next row would actually have 9 orbital shapes. But you know how the S's was just a sphere and the P, I talked about having that fold in it? Look how different these look from our book. They're bigger lobes. They're just different calculations, whether that's probability was 90% or 95, it changes the overall size of that. But it is still, we call it a dumbbell shape. It's kind of got that fold to it. And down on the D's, it's just done that again. So if you imagine somehow twisting this again, we get the 4 little balls. And this is a neat one here in the middle. What's mathematically happening is we took the P or the S orbital, twisted it to create a lobe like this, and then we untwisted it, and it didn't go back to this. It created a little weird donut in the middle. And there's a mathematical reason why all this happens. It's just interesting pictures right now. It doesn't help us predict how the atom's going to behave or do anything at all with that. And proving these guys, the shapes are like this, is kind of a challenge, because this is a mathematical reconstruction of theories and not necessarily something we can visualize. Because the atom's obviously really, really small, and we're looking at all of those electrons in an atom moving around at a ridiculously fast speed. Technically speaking, when you average them out, most of the time it's going to look like a ball anyway, because of the sheer number of electrons. Just actually imagine overlapping these guys, which is what we see on our little thing. Some of them, you're not going to be able to see these guys individually. So that's why we don't need to focus on it too much. Alright, that gets this chapter done. Thank you very much.